All right, for the last video on sections 10.2 and 10.3, we're going to look at question 13, which says, find the first three non-zero terms of the Maclaurin series for each function, then write the series using summation notation and determine the interval of convergence. Okay, now I make a note here at the top that says, for this type of question, you can use the list of Maclaurin series found on page 690 in the textbook. Okay, also note that I've included the most important series from that list on the 10.4 worksheet, which you can see right here, and this worksheet is up on Canvas. All right, so let's go ahead now and jump into part A, where f of x is the arctangent to 3x. And now recall from question 7, we showed that the arctangent of x is equal to this series x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on. And this series converges to the arctangent of x, right, for all x that's greater than or equal to -1 and less than or equal to 1. Okay, so now the idea is to simply replace x with 3x to generate the series for the arctangent of 3x, and that's exactly what we're going to do here. Okay, so I get that the arctangent of 3x, this is the sum of -1 to the n, that's right here, and now instead of just x, I have 3x to the 2n plus 1, and then we're dividing by 2n plus 1. And note that the condition on x now is that 3x is greater than or equal to -1 and less than or equal to 1. All right, so let's break down this expression that we're summing as follows. So I have a -1 to the n, then I have a 3 to the 2n plus 1, and then an x to the 2n plus 1. And we're dividing by 2n plus 1. And this condition on x now, by dividing by through by 3, I get that x is greater than or equal to -1/3 and less than or equal to +1/3. All right, so now I want the first three non-zero terms of the Maclaurin series, right? So let's go ahead and expand this series. And so note when n is 0, I get -1 to the 0, that's +1. This will give me a 3 to the first, which is 3. This is an x to the first, which is x, and then the denominator is 1. Okay, so when n is 0, I get this term 3x. When n is 1, I get -1 to the first, that's -1. Then I get a 3 cubed, an x cubed, and then the denominator is 3. So this simplifies to a -9x cubed. When n is 2, I get -1 squared, so that's a +1. This is a 3 to the 5th, an x to the 5th, and I'm dividing by 5, so I get plus 3 to the 5th, x to the 5th over 5, which simplifies to 243 over 5 times x to the 5th. All right, so these are the first three non-zero terms. So in summary, here's our answer in summation notation. Here are the first three non-zero terms, and here's the interval of convergence written in interval notation. All right, cool. So now let's go ahead and jump into part B. Right here, f of x is -2 plus 5x, all to the negative first power. So first note that this negative exponent, right, is really just saying take the reciprocal of -2 plus 5x. So this is equal to 1 over -2 plus 5x. And this expression is of the form a over 1 minus r. Okay, so I'm thinking about geometric series here. Now, in order to write it in that form specifically, I'm going to go ahead and factor out this -2. Okay, so there's going to be a 1 there. Now I'm going to have a -2 downstairs. I'm going to move it upstairs here, so I get a -1/2. That's going to be my a value. And then factoring out the -2 from -2 plus 5x, that leaves us with a 1 minus 5/2 x. All right, so now, okay, noting that a over 1 minus r is equal to the sum of a times r to the n, where the index n starts at 0 here, which in expanded form is a plus ar squared, and so on. Right? We have equality here when the common ratio r is strictly less than 1 in absolute value. And as I just noted, right, in this case, a is -1/2 and r is 5/2 x. Okay, what I'm going to do now is substitute these values into this series, and I get the following, right? So this expression is equal to the sum of a, which is -1/2, times r to the n, right? 5 halves x to the n. And the condition here on x, right, is that this common ratio r, which is 5 halves x, must be strictly less than 1 in absolute value. All right, so now let's go ahead and rewrite the expression we're summing. So I have negative 5 to the n up in the numerator. Then I'm going to get a 2 to the n downstairs, but then that's being multiplied by this 2, so I get a 2 to the n plus 1. And then here I get the x to the n. And this condition on x, note, is equivalent to saying 5 halves times the absolute value of x is strictly less than 1. And so dividing both sides by 5 halves, I get that x is strictly less than 2/5 in absolute value. All right. So this is our answer in summation notation. Let's expand it to get the first three non-zero terms. When n is 0, I get negative 5 to the 0, and that's just a 1, over 2 to the first, that's a 2, and then I get an x to the 0, which is 1. So I get negative a half when n is 0. When n is 1, I get minus 5 to the first over 2 squared. So that's minus 5/4, and then I get an x to the first. So that's minus 5/4 x. When n is 2, I get minus 5 squared. That's minus 25 over, this is going to be 2 cubed, which is 8, and then I get an x squared. All right, so those are the first three non-zero terms. And so in conclusion, here's our answer in summation notation. Here are the first three non-zero terms, and here is the interval of convergence in interval notation. All right, so then let's go ahead and jump into part C. We actually did an example really similar to part C. This is back in question 6. All right, we're looking here at f of x is 9x cubed times the natural log of 1 plus 4x. And recall this result. It said that the natural log of 1 plus x is equal to the series x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. And this series converges to the natural log of 1 plus x for all x, such that x is strictly greater than negative 1 and less than or equal to 1. Okay, so now I'm just going to replace x with 4x, right? So let's do that. So I have 9x cubed times this natural log, and now I'm going to replace the natural log with this series, where x now, in the series for the log of 1 plus x, now, right, is replaced with 4x. Okay, also note that the condition on x is now 4x is strictly greater than negative 1 and less than or equal to 1. All right, so just like the others, let's write the expression that we're summing, right, in following form. So I'm going to distribute the 9x cubed. So I'm going to get this 9 here. I have negative 1 to the n plus 1 there. Here I have a 4 to the n. I'm still dividing by n. And then I have an x to the n there. And then when I distribute x cubed, that bumps this up to x to the n plus 3. All right. Now for the condition on x, dividing through by 4, I get that x is strictly greater than negative 1/4 and less than or equal to positive 1/4. All right, cool. So then let's go ahead and expand. When n is 1, we get 9 times negative 1 squared times 4 to the first over 1. So that's 9 times 4. And then for the x, I get an x to the 4th. So I get 36x to the 4th when n is 1. When n is 2, we're going to get 9 times negative 1 to the 3rd, and then 4 squared, that's 16, over 2. And then for the x, I get x to the 5th. All right, so this simplifies to minus 72x to the 5th. And then finally, when n is 3, right, we get 9 times negative 1 to the 4th times 4 cubed over 3. So this is what? 9 times 64 over 3, and then this is a x to the 6th. And that simplifies to plus 192x to the 6th. Okay, so on and so forth. Right, so in conclusion here, we got our answer in summation notation. There are the first three non-zero terms, and here is the interval of convergence in interval notation. All right, great. Well, that is going to do it. Thank you so much.